What a horrible place to end the screencast. I'm sorry. So I get f sub n of x. I'm proving, by the way, that this result is true independently of this theorem. This theorem says that if you prove that the derivatives converge uniformly to some function g, which I'm saying is 0, which I prove up here, and if f sub n, that should be sub n of x naught converges for some x naught, I'm sure I'm picking x naught equal to 0, you could actually pick anything, then f sub n of x naught equals 0 squared. So you get a bunch of zeros, which, no surprise, converges uniformly to 0. All you do is let epsilon be bigger than 0 and let n equal 1 because it's going to be tough for it not to converge to 0. And now this theorem says that you automatically get fn goes to f with f prime equal to g. I'm going to prove it just to show you that the theorem works, but you don't normally need to do this because that's the point of the theorem. Let epsilon be bigger than 0. By the Archimedean principle, there exists a capital N such that 1 over n is less than 2 epsilon. For all little n bigger than or equal to n, this minus the limiting function. So here now my f is equal to 0. Well, subtract 0, you get that. X squared, it's less than or equal to 1 squared over 2n, which is 1 over 2n, which I can separate like that. 1 times 1 over n is less than or equal to 1 half times 1 over n, which is less than or equal to 1 times 2 epsilon, which equals epsilon. So I proved that this converges uniformly to f, and if my f is 0 and my g is 0, I get f equals 0, f prime is equal to 0, and that of course equals g. So I've verified that the theorem actually does work. Again, the point of the theorem is though that you don't have to do this step, but I did it anyway just to prove it. Now so I'm done with the example. Let me give you a non-example that's very similar. I'm going to give you an example of a differentiable sequence of functions that goes to g, and I'm going to pick one that doesn't have this x naught. So at no points is it going to converge, and then this is not going to be true. So here's my example. I'm going to let f sub n equal x squared over 2n, which almost looks exactly what I have here, except now I'm just going to add plus n. Now what you get is fn prime. To take the derivative, you're just going to get, you get x over n plus 0. Because the n is just a constant as far as x goes. And we already showed that that converges uniformly to 0, which I'm going to call g. Now I'm going to claim that no x naught works. And why does no x naught work? Well, if you look at this, this is just going to keep on going up and up and up and up. So let me show you this graphically, and this is not going to be a rigorous proof. This is just going to be I'm just going to show you what happens. So here's what I have, x squared over 2n plus n. And look, I have kind of a parabola shape like this. Now when I animate it, no, it's just going to keep on going up and up and up and up and up. What am I doing? Here you go. So I'm going to animate it. It just goes up. It goes up and it flattens out and is still going up. It's out of the picture. And now it's going to keep on going up forever. So notice, at no point is it going to converge because it's going to go off to infinity, because this part here is going to go to 0. That part here is going to go to infinity. So you're going to go up and up forever. So this really is a function where no x naught works. And notice that this function is not going to converge to any particular function, The fn's are not going to converge to an f because it's going to keep on going up, basically become a straight line that's going up to infinity. So that's why this is not an example. And we are done.